Jeff Zurita, Deepwave Digital, here to talk about the Artificial Intelligence Radio Transceiver. It's a software-defined radio with an onboard GPU. So quick overview, the AIRT, as we call it, has several models in the product line, mostly differing in housing, FPGA capacity, and ultimate environmental application. You see a ruggedized version up there, a bare board, and a desktop model for development. In general, they all have the same architecture, an RF transceiver chip by Analog Devices, an FPGA, and an NVIDIA Jetson GPU system on a module. Quick overview of specs. So frequency range goes from 300 megahertz to 6 gigs or down to 30 megahertz with an optional daughter card. Sampling rate is 125 megasamples per second on each INQ, so you get about 100 megahertz of usable bandwidth to process. Swap it consumes at worst case 25 watts, mostly when it's starting up, but you get like 15 watts under normal operation. Normal varies, of course, depending on what you're doing on the GPU and the processing units. And we're calling it TRL7 because it's been deployed, more on that later, but it's been deployed in an outdoor environment in full weather. Pausing this thing. Okay, what's so great about this architecture, about having a GPU system on a module as the main processing unit? The advantage is that the NVIDIA Jetson system on a module includes both GPU and CPU processing elements, and they share the same memory. Normally, if you have a software-defined radio at the end of a bus and a GPU at the other end of the bus, they have to do a lot of data transfer over the bus, copying data from one to the other, because each CPU and GPU have separate memories. So this, needless to say, adds delay. We've observed up to 50 milliseconds of latency just in doing all this data copying back and forth. But if you have a system on a module where they're sharing the same memory, you obviously don't have to do that. Both CPU and GPU have access to the same memory, and this saves a lot of transfer and latency in that case. I want to touch upon the software stack very briefly. The AIRT radio comes with a full operating system. We call it AirStack. It's based on Ubuntu, so you can do everything you can do in Ubuntu. But it also includes all the hooks needed to access the processing units, all the software bindings and drivers and whatnot. So right out of the box, you can start programming on the CPU or GPU. As for application programming interfaces, it supports just about every library. I'm sure there's a bunch there that most of you are familiar with already. I could do processing on the CPU, processing directly on the GPU, things like CUDA, and you can do neural networks. Oh, and again, this thing is running with a mind of its own. This is the obligatory, let's start the video. Except it won't start. All right, obligatory signal classifier. A neural network is classifying radar signals. You can actually see this being run in real time at our booth at the exhibit hall. But we developed this neural network. It runs natively on the AIRT without any supporting structures other than power and antenna. We really got to pause this. And before we leave the neural network, I just want to hit upon the ROC curve in the lower left, showing that you get great classification results even at negative SNR ratios. You get down to about minus 10 dB SNR before performance starts to fall apart. This is just a toy application done with synthetic data in our lab, but it did lead to an application that we deployed later on. I guess the other side of the coin is if you can do machine learning and artificial intelligence on the radio signals, why can't you do it on the data content of those radio signals? And this is our other toy application. It's a speech-to-text application based on GMRS radio. So if you transmit GMRS frequencies, you probably know this already, but it's a narrowband FM modulation. You can use the radio to demodulate the data. You get raw audio, and you can process the audio to get a speech-to-text application, again, all natively on the AIRT. Wow, I'm really keen on keeping to those 5 minutes because the slides keep moving automatically. Anyway, so before we leave it, the speech-to-text is, again, an NVIDIA model that takes raw audio and gets text output, but the audio comes from a GNU radio script that does GMRS FM demodulation. And I wanted to talk about a real application. We talked about that radar classifier earlier, and that led to this application on the CBER system, the Citizens Broadband Radio Service. You probably know is a shared spectrum service. There's a primary user and a secondary user. There's a telecommunications company that's using the spectrum as a secondary user, but when the primary user is using the spectrum, they have to vacate the spectrum and allocate the user to other channels. And the way they do this, they use the artificial intelligence radio transceiver to detect the primary user. It's the Navy radar system. The Navy doesn't like to schedule usage of their radar or tell anybody when and what they're doing it. So the service provider relies on the AIRT trained neural network to detect that the radar is operating. It informs the network operator, and they can allocate the users to other channels. And what's seen there, the photograph to the lower right is Keybridge. They're the spectrum, environmental spectrum sensor provider. The AIRT is deployed inside that box along with GPS to perform GPS discipline oscillator functions and whatnot. And that's all I have. I'm clocking in at 5 minutes and 8 seconds. Do we have any questions? Okay. Well, if there's no questions, come visit us. We're at the booth. We're here all week, as they say. Thank you for your time.